were very nervous from the mobile internet service and the WiMAX. Because WiMAX is just like wireless LAN, but it covers a much more larger area. So you can cover the entire city, for example, with a WiMAX service, where you can make voice over IP phone calls. And so there was a big competition, and in fact, because when you go buy your phone, you don't buy the phone from Nokia or from Ericsson. You buy it from a mobile phone operator like Mobil or Vodafone or something like that. So the mobile companies started to say, okay, we're going to try to mix WiMAX with cellular, and they introduced the LTE, which is based on off-the-M modulation. I don't know if you have covered these things, but very quickly I just want to show you that this kind of war between 3G and WiMAX is ongoing in many places right now. So if you look at the different wireless services, you have of course the personal service, you have the local area network, the wide area network, and the WiMAX. So the cellular people would like to, or the WiMAX people would like to kind of push the cellular services away, whereas the cellular people would like to kind of reduce the WiMAX service. And then, so there was this war going on, and then I just wanted you to get the message here that the technology alone is not the issue, but there's business models and money to be made, and that basically controls the technology actually. So the technology is, in a lot of ways, is driven by the business. People basically started looking at a way to combine, or maybe the companies started to look for a way to contain WiMAX. So they introduced this LTE thing, which actually it's a WiMAX downlink from the base station to the mobile, and it's a downlink with a wideband CDMA. So off-the-M is well known for multipath fading, combating multipath fading and quality of service. So they basically combine, and this is now being developed in many places. It will be in service in about 4 years from now, by 2013 or 2012. So let's skip that quickly and then go. This is what I mentioned earlier, that everybody wanted to achieve this higher performance price ratio, so that you can have more services, but you don't have to pay for it a premium price. You can pay a smaller amount. So one of the most significant human achievement, and of course Senate spoke about that earlier, is tremendous scaling that happened over a very short span of time, maybe 10 years or so. The phone went from a very large size to a very small size. So I'm taking here the Ericsson products just to show you the radio part in particular. You can see the 1992. We have this logic board, and then we have the RF board on the phone. The phone was large, and it was basically one band and two boards, and we have the 5,000 square meter for the RF board and 5 volts. But very quickly, the phone started to go down to 4,000 square meter RF, and then still 5 volt in 1994. Now it became dual band on one board, and RF parts are almost half what it used to be like 3 years before, and the voltage is now 3.6. And this is actually the T28 was the first zero AF radio. I don't know if you know, this is a radio that actually gets rid of so many off-chip components. You have a lot of components now being integrated, and it's the same phone that Nokia also produced around the same time. And it's a dual band. It's a single-sided mounting, so you don't mount on both sides. You mount only on one side. And then, if you look over a very short span of time, the scaling was enormous. You know, and of course, Dr. Ismail spoke about that, about the scaling, mostly because of the digital. You look at the 3G phone, and you see that you have, of course, wideband CDMA, you have GSM, you have Bluetooth. It's very difficult to scale beyond this, extremely. And the main bottleneck, the main obstacle is the radio part. You know, the radio part is main thing. Of course, everything is being done in CMOS technology, nanometer, and then except for some parts like the power amplifier, and primarily it's done, could be done in CMOS for short range, but for long range, people use SEGI or gallium arsenide. And of course, with the MIMO technology, these things became extremely important. And you see the companies that are doing like radio power amplifiers, you see them doing very well these days, such as RFLD or Analytics in the US. So I'm going to skip some slides here because I don't want to go through all these things, but I want to show you a radio that we are developing for LTE multi-band radio. So you can see the level of complexity here for this radio. So this is your digital part, where you have all the modulation, demodulation, coding, authentication, all these different things. And you have the antenna, of course, here. And then you have the receiver side, and then this is the transmitter side. So it's a multi-band radio, and also it's done in MIMO. So you can imagine the complexity that we're talking about. And so the way things work is that you have these different bands, from 2.5 gigahertz down to 850 megahertz. And then you take the RF and you convert it down to baseband here, with some A to D converters and some filters and AGC. And then you also have a very sophisticated, complex what we call fractional N PLL, or a synthesizer, that allows you to cover all these different bands, basically. So this is a zero-F architecture. And to develop this type of radio, it could take a very, very long time to get it to work. You know, so, and typically today in industry, you have to spin this radio many times, maybe 3 or 4 times to get it right. You know, but I don't think this is, particularly when you go to nanometer, like you go to 45 or 75 or to 22, it becomes extremely difficult to do that. It's very expensive. So our vision, basically, for this is that most of these different bands will be done in one radio, and we will have in the radio some digital smarts. By these smarts, you will be able to control the radio part and restore the performance, make the performance work from the first time, without having to spin it over and over, right? And we have been basically looking into the critical parts of the radio, like the synthesizer and the RF front end. You know, these are the different parts, these are the most difficult parts of the radio, and that's most of the problems, basically, reside in these parts. Okay? So why do we have to do that? As I pointed out, you want to reduce the cost of developing a chip, you know, and we're now looking at high volume, low cost type of products. So you want to reduce what we call NRE, or the non-recurring engineering cost, faster product development, and so forth. You know, so that your engineers, instead of being, you know, busy fixing mistakes, they could be developing the new product instead. So just to give you an idea about the design, you know, I'm going to take a startup model, not a large company. When you do a chip, radio chip, basically it takes about 4 weeks to firm the specs, and then you do a design for 3 to 6 months or so on the entire radio. We just did one for DVB-H, and then you do layout, and then you keep going back and forth between the design and the layout, and then when everything is done, you fabricate. It takes about 8 weeks to get the chip back, because the fabrication is done primarily in Taiwan or one of the big foundries. And then you test, and then you compare to the performance. You know, so that takes anywhere between 6 to 9 months. You know, so if you have the chips come back and you have a problem, then you have to repeat this thing again. So it's very costly, particularly when you design things in nanometers. You know, that you have to pay to do a full mask. You have to pay a significant amount of money. So you don't want to do that. You want to get it right from the first time. The reason for this problem, basically, that this chip doesn't work, is you have random process variations, you have mismatches, you have electromagnetic on-chip coupling when you do the layout, and inaccurate models, you know, and substrate noise coupling. But